think what helps is that yeah, like around 8.
Oh, I need to change the setting on Zoom. Right now it's blurring the background so they won't see me when I'm giving the talk.
Okay, so I shouldn't say anything.
See, you says podcast on YouTube live.
Oh, it is. Already.
Yeah.
Already? Okay.
That did not. Over here. Okay. Like a little bit more than an hour, maybe. Yeah. Okay.
Okay. Welcome everyone to Harvard CMSA Fundamental Mathematics and Mathematics. I'm happy to have Abijith Krishnan. He will be speaking about his joint work with Nc from MIT. Certain defect in the 3D full model. If my new audience, please feel free to interact with Abijith at questions. Let's welcome Abijith.
Hello, everyone. Thank you for having me and thank you for your work organizing, Juvin. So today I'll be talking about a plane defect in the 3D EON model. This talk is based off of work that was put on the archive a few months ago in collaboration with my advisor, Max Militsky. All right, so let me first start off by talking about the general setup of boundary or plane defect criticality. Let me get rid of this. Is there a way to hide this? All right. Okay, that's fine. So we'll start with a system whose bulk is tuned to its critical point, and we'll examine the different universality classes that can arise on the boundary. In general, deep in the bulk, the bulk CFT scaling relations will hold for bulk operators. So for example, operators O in the bulk might have some scaling dimension delta. However, when we go to the boundary, the operators, when promoted to the boundary, might have a different scaling dimension delta hat. And in general, bulk CFT can have multiple boundary or plane defect universality classes. So the setup of boundary and plane defect criticality was studied extensively in the 1970s and 80s, but recent numeric and analytic developments in conformal field theory and on symmetry protected topological phases have revived interest and progress. For example, the numerical conformal bootstrap has allowed us to get results in boundary criticality that we would not have been able to get in the 1970s and 80s. And I'll briefly mention those later in the talk. Additionally, the question of whether a gapless edge mode of an SPT survives as you tune the SPT to criticality is a question in boundary and plane defect criticality. So with that, yeah.
It's time to say that boundary bit one more slide. So the boundary criticality and bulk criticality somehow the relation hold. How do you mean precisely?
So I mean, if you take if you take operators OX and OY here that are very far away from the boundary, the correlation function looks as if there is no boundary. Yeah, so just in the limit of being far away from the boundary or defect, the correlation functions look like the bulk correlation functions you'd expect in the absence of a defect or boundary.
On the head one is the boundary.
Yeah, the hat. So yeah, so in this talk, I'll refer to hat as boundary usually if it's on an operator.
How do you try to show in these two figures? Maybe just say this.
So this is just the general setup of the hat operators, but here I'm saying that the hat operators have different scaling dimensions than the operators without a hat.
You say the same.
They have different. So there's a delta hat here and a delta here. Yeah.
But then on the right hand side, you have a bigger bulk, but somehow you still use hat.
So this is the plane defect. The red line here is the red plane is a plane defect. Yeah. Oh, yeah.
The whole hat is out of second.
Yeah.
But that plane is the like virtual one, or is that the physical?
It's so I'll talk about the specifics of what it looks like for the 3DON model. In general, you should think of it as just some perturbation acting along. There's some perturbation along the plane. Yeah. All right.
But that is intrinsically in that plane dimension of it consists of a lot of the local operator.
Yeah.
This is local.
Yeah.
That's local operator, like extend operators, or just local operator.
On the plane, yeah, it's local operators on the plane. I guess I'll jump ahead, but like in the case of the 3DON model, we'll just consider changing the couplings between spins on the plane defect. That will be our perturbation.
A plane defect is not, in that case, it's not like topological.
Yeah, it's not topological. All right. So let me start off by just talking about the system that we will be studying in this talk. It's the classical 3DON model. And to recap, it consists of spins on a lattice. These are classical spins. They are n-dimensional and their norm is fixed to be 1. Our Hamiltonian has nearest neighbor couplings between the spins. And in the bulk, we'll take the nearest neighbor couplings to be k. In the continuum, we can write the action as follows, where phi is the order parameter for the spins. Lambda is a Lagrange multiplier that fixes the norm of phi, and G is our bulk coupling. So now that I've talked about the general setup, let me go into the different results for the boundary story for the 3DON model. The boundary story has been studied in the past few years, and a lot has been discovered about the phase diagram for the 3DON model with the boundary. So the first perturbation we could add to the boundary is applying a magnetic field to the boundary. When we apply a magnetic field to the boundary, regardless of the bulk coupling, the boundary will order. And so we get this phase diagram over here. The y-axis corresponds to the inverse of the bulk coupling, so it acts like inverse temperature. The x-axis corresponds to the magnetic field. And we see that regardless of the bulk coupling, if the boundary, as long as the magnetic field is non-zero, the boundary will order. And thus this bulk transition happens in the presence of an ordered boundary. And this universality class is called the normal universality class. Now let's ask what happens if we remove the magnetic field and instead we change the coupling along the boundary. So we'll change it to some value K1. It turns out that we get different phase diagrams for different values of n. So let's go case by case, starting from n equals 1 and increasing n. So when n is equal to 1, our spins are either just 1 or -1 because their norm are fixed to be 1. So we just have a 3D Ising model with a boundary of a different coupling. Now we know that if the bulk coupling is very small, if the boundary coupling is very large, the boundary will still order for an Ising model. And thus we have, in this regime, a transition between boundary disorder and boundary order. And this green line is the boundary transition here. Now we can ask what happens once we tune the bulk to its critical point. On this side of the phase diagram, the boundary is disordered, and we end up getting what's called the ordinary universality class, where the spin-spin correlation function falls off as a power law at the bulk critical point along the boundary. On this side of the phase diagram, the boundary is ordered. So even as we tune the system to its bulk critical point, the boundary will stay ordered. And thus we get what's called the extraordinary universality class, where the spin-spin correlation function goes to a constant. And this point right here, called the special fixed point, is just the transition between the ordinary and extraordinary universality classes. Any questions about that? Yeah.
I think I asked Max when this a while ago. And he explained for some reason you cannot have a bulk order boundary disorder in phase diagram.
Yeah, so I think
my question follow up is that because sometimes when you choose something order or disorder, maybe the operator or the symbol you are carrying for, but a lot of time you might change something disorder to or something disorder to another operator disorder. So I'm wondering is that so why is that not possible to find the description very old this?
so. I think in this particular system, because the boundary is just coupled to the bulk through this term, when the bulk is ordered, the bulk just acts as a magnetic field for the boundary. I think in general, you might, like, if you think about quantum systems, you might be able to add a perturbation that makes the boundary disordered. But in this particular setup, in this classical system, since there's nothing else acting on the boundary, the bulk just acts as a magnetic field. Yeah. Okay. So now let's increase n by 1 and see what happens for n is equal to 2. So now we know that if the bulk coupling is 0, the Merman-Wagner theorem forbids the boundary from ordering. And for n is equal to 2, we have the XY model. So instead, we get quasi-long range order along the boundary for sufficiently large values of the boundary coupling. So here we still have a boundary transition, but it's between boundary disorder and boundary quasi-long range order. And we can ask the same question. What happens as you tune the bulk to its critical point? It turns out we still recover the ordinary universality class, but on this side of the phase diagram, we get a very unique correlation function between the spins that does go to 0, but very slowly. It falls off as 1 over log x to some universal power. And this universality class, we call the extraordinary log universality class. It's really unexpected, and this extraordinary log universality class will be present in a lot of this talk. Finally, or we can ask what happens if we increase n greater than 2. Now, there is no boundary transition here at all, but it turns out that below the critical Nc, we still get the extraordinary log universality class in the special fixed point. And this is surprising because there's nothing different about the boundary on this side of the phase diagram and this side of the phase diagram. But it turns out we still get the extraordinary log universality class. Finally, as we take n to infinity, the special and extraordinary log universality classes disappear, and we just end up with the ordinary universality class. So that's the story of that's the boundary story for the 3D-ON model. Yeah, Darius.
Is there any intuition for why at large n the extraordinary log is disappeared?
You will see later on in the talk. Yeah. So
Hey,
you might be asking, is NC non-trivial? Is it greater than or equal to 3? And while we don't know analytically the exact value of NC, there's evidence that NC is greater than or equal to 3. For example, there have been Monte-Carlo simulations that have behavior consistent with the extraordinary log universality class. Additionally, there is a predicted relationship between the normal and extraordinary log universality class, which I'll talk about later in the talk. And that was verified for n is equal to 2 and 3 through Monte-Carlo simulations. And finally, the numerical conformal bootstrap estimates that NC is approximately 5. And that was the numerical result that I was alluding to earlier. All right, so that was the boundary story. Let's move on to the plane defect story. What are the different universality classes we can get in the plane defect story? So just like in the boundary story, we can add a magnetic field to our plane defect as a perturbation and look at that universality class. Now, at the fixed point,
Maybe Hamiltonian, like your description, what's the plane defect? Just make sure.
So this is the Hamiltonian here, and then you're just applying a magnetic field to everything on the defect.
Some plane.
Yeah,
And that's feasible in experiment also.
I'll talk about experiments later. Yeah. Right now, everything is just everything is a little bit abstract right now, but I'll talk about the different universality classes that can appear in experiments. Yeah. So if we apply a magnetic field to the plane defect, the spins on the boundary or the spins on the defect will order. And because we only have nearest neighbor couplings, we can just separate our system into 2 halves where the boundary of each half is ordered and they don't really talk to each other. So we can think of the normal plane defect universality class as 2 normal boundary universality classes. Now let's remove the magnetic field and ask what are the so if I start with this plane defect, all the spins being ordered, everything directly above the spin, we'll just see that there's spins being ordered below it, and everything below this spin, we'll see that there's spins being ordered above it. And so these two halves of the space don't talk to each other because all they see is a plane of ordered spins. And that's why you can split it up. Yeah.
Well, because the component only have the
Yeah. All right, so let's remove the magnetic field. Instead, let's just change the coupling along the plane defect. The easiest thing we can do is set the coupling along the plane defect to equal the bulk coupling. And at the critical point, we get the special fixed point. And this is just the fixed point that you would expect if there's no defect at all. Then we can ask, what happens if we add a perturbation to the special fixed point? Is the special fixed point stable or unstable? And the way we can do that is by adding a perturbation parametrized by the thermal operator, which is the lowest dimension ON singlet scalar that we can add as a perturbation. The dimension of this operator is less than 2. So it's a relevant perturbation, and thus this constant C grows under RG flow, and thus the special fixed point must be unstable. we'd expect that C greater than 0 and C less than 0 corresponds to two different universality classes. And C greater than 0 is just the ordinary universality class. And the C less than 0, we'd expect it to be something different. So we'd expect it to be extraordinary log, but we don't know for sure. So let me first talk about the ordinary universality class very quickly. For the ordinary universality class, the coupling along the plane defect is 0. And so we can do the same trick that we did with the normal universality class and separate it into two ordinary boundary universality classes.
Basically, what's the sign of the small quotation epsilon? Because C choose particular plus or minus, but the larger, smaller than 0 will become different cases. But epsilon is arbitrary perturbation.
So epsilon here is the thermal operator. So it tells you the energy. It's a perturbation to the energy. So when C is greater than 0, it's as if you're adding a large energy to the defect, and that's why we get the ordinary universality class.
So epsilon is positive.
Well, epsilon is a field.
But you know the meaning for the sign of the C will change with respect to epsilon as well. Because C is the term is C.
Yeah, so epsilon is the operator that inserts energy. So epsilon is a specific operator. It's just the epsilon operator for the ON CFT.
But when you write of X is XY plane,
Yeah,
right?
yeah.
But
Oh.
I guess how it is. Is that the division in a certain direction? Or
No, epsilon is a scalar. So we're just applying it to the plane. Yeah. So yeah, as I said, the ordinary plane defect universality class can be written as two ordinary boundary universality classes.
scalar is respect to the own model of that field. Is it by field or what field is it?
So it's a primary operator, and I'm not sure exactly how it fits into the OPE expansion of phi off the top of my head. Yeah,
Like consists of the field from the one.
yeah.
It'll be nice. Exact term.
Yeah, and I think like the actual coefficients of the OPE expansion are not known in general, so that's why I didn't write it down. Yeah. All right. So the other universality class that we think is the extraordinary log universality class, instead of being, since the coupling along this plane is very large, we can't just write it as two ordinary boundary universality classes. We can split up the system into one half space, the plane defect, and another half space. So we can write it as an ordinary universality class coupled to a plane defect coupled to another ordinary boundary universality class. This is just to help us visualize what's going on in this other universality class. Are there any questions about this? Because I think this picture will be important.
Is there a latest model version of what you're doing there? Maybe no, nothing.
I mean,
produce some coupling right now between two planes. Right?
yeah, so you can think of the defect. We're separating out the defect layer from the two half spaces. And then these are the two different half spaces with their own lattice Hamiltonian. And then there's an extra coupling to this intermediate defect layer.
But you enlarge the Hilbert space.
No, we're not enlarging the Hilbert space. It's just re-expressing the defect layer as a separate layer instead of attaching it to the bulk.
But I think like first you are separating the plane defect into two boundary conditions, and then you introduce additional layers such that they have some coupling. Naively, it looks like you introduce multiple freedom then. If you think of the system as bulk
defect bulk. That's what this picture is, right? It's still bulk, defect, bulk here. Yeah, so it's not, we're not adding any extra degrees of freedom. Yeah,
Oh, the layer just next to the.
yeah. So the questions we have for plane defect criticality: for what n does the extraordinary log universality class survive? There was a critical NC for the boundary case. Is there a critical NC for the extraordinary log case? Additionally, what is the phase diagram at infinite n and for large finite n? Do these results line up with known theorems about boundaries of 3D CFTs? And finally, what quantum systems can realize the extraordinary log universality class? And that was related to the question you asked earlier about experimental realizations. All right, so let's go back to the picture that we had of the potentially the extraordinary log universality class. You're writing it as two ordinary boundary theories plus a nonlinear sigma model in between them. And this is what it looks like as an equation with an action. This is the extraordinary log action, where we can write it as two copies of the ordinary boundary universality class, a nonlinear sigma model, and then a coupling between the two layers, between the layer and the two ordinary universality classes. Here, instead of labeling the fields as phi on both layers, I'm just labeling them as phi1 and phi2 to correspond to different half spaces. So if the extraordinary log universality class, the G, the coupling, and the nonlinear sigma model should flow to 0. If it doesn't exist, G will flow to infinity. This nonlinear sigma model will no longer be ordered, and then we will flow, then we should just get the ordinary universality class. So we can.
G flows to 0, what determines the power of the logarithm to the correlate?
We will see that.
Is it related to these parameters?
Yeah, it's related to S, but we'll see exactly how that happens. All right, so the way we can do this is we can go to the small g limit. We can freeze the direction of n to point in the unit, in a particular unit vector direction n hat, and expand around its fluctuations. This is typically what we do for the ON nonlinear sigma model. And so when we rewrite this term doing that, we end up with this term over here, and then this term with the fluctuations. Now, n hat is a fixed unit vector. So we're effectively just applying a magnetic field to each of the boundaries of the ordinary universality classes. And remember here, phi1 hat and phi2 hat are just the boundary versions of the phi1 and phi2 field operators of the ordinary universality classes. But the universality class that has a magnetic field is the normal universality class. So really, we can rewrite our action as two copies of the normal universality class, S pi, which is just the nonlinear sigma model written in terms of the pi fluctuations, and then a transverse coupling between the nonlinear sigma model and the fields on the boundary of the normal universality class. And the reason I say transverse is just because it's pointing orthogonal to the direction of the magnetic field of the normal universality class. And this is what it looks like as a picture. So we start with what we think is the extraordinary log fixed point, and we write it as two normal boundary fixed points plus a nonlinear sigma model, where now instead of coupling in all the n directions, we have a transverse coupling perpendicular to the boundary magnetic field.
What's the difference between the pi field and n field and n field earlier in the slide?
So pi is just like, imagine freezing the vector n to point in the nth direction. The pi fields are the components of the fluctuations of n around that nth direction. Yeah. All right, so why did we go through all this trouble to write the extraordinary log universality class in terms of the normal universality class? Well, it turns out a lot is known about the normal universality class. In particular, we know the form of the OPE expansions in the normal universality class. So first, the important results from the normal universality class is first that if the field is frozen in the nth direction, the component of phi n, the nth component of phi, falls off as a power law from the defect. And additionally, there's this relationship, there's this correlation function relationship for the components of phi that are not in the nth direction. And here, a sigma and BT are just universal amplitudes. I will say that here, M is just referring to which half space that you're in. So M equals 1 just refers to being in the bottom half space. M equals 2 refers to the top half space. Now, the difference between the extraordinary log universality class and the normal universality class is that there's actually no symmetry breaking field in the extraordinary log universality class. So that means the extraordinary log universality class must preserve ON invariance. So we can use this to constrain what S has to be. If we rotate n hat toward the one direction slightly by some value alpha, we expect by ON invariance that the expectation value of phi 1 also falls off as a power law with amplitude proportional to alpha. And additionally, if we compute this expectation value from perturbation theory with this term in the action, we should get the same answer. And this constrains what S has to be. And we find that S is equal to a sigma over 4 pi BT. The actual value of S is not super important. The important takeaway is that S is constrained by ON invariance. So yeah, S is fixed by ON invariance, and it affects the RG flow of the G in the nonlinear sigma model. And we can just go through perturbation theory and compute this beta function. When we do that, we find this form for the beta function. Importantly, there's a factor of 2 here because we have 2 copies of the normal universality class. And with this correlation, with this beta function, we can check that its coefficient is positive for both n equals 2 and n equals infinity. And it turns out that it is. So G flows to 0 for both n equals 2 and n equals infinity. So it seems like we're in the same universality class for all n greater than 1. In contrast, in the boundary story, there's only one copy of the normal universality class because we just have only one half space below the boundary. And so there's, instead of a factor of 2 here, we have a factor of 1 in all these expressions. There we find that the coefficient is positive for n equals 2, but it's negative for n going to infinity. And that's why there is a critical NC for which the universality class changes in the boundary story, but not in the plane defect story. And here is just how we get extraordinary log from this positive coefficient. So recall that this is our defect Hamiltonian. This is what the defect action is in the absence of the bulk. And so with no coupling to the bulk, we get the result from Polyakov for the beta function. When we do add a coupling to the critical bulk, we find that beta of G equals alpha times G squared, where alpha is greater than 0. And to recap, that just means that G flows to 0 as our RG scale increases. When we substitute this into the Callan-Szymanski equation, we end up getting this 1 over log x to q correlation function. And we find that q is equal to n minus 1 over 2 pi alpha. And that was the relationship that you were looking for between S and q. Thus, we recover the extraordinary log universality class for alpha greater than 0. Or in other words, for all n greater than 1. So yes, we've answered that the extraordinary log universality class survives for all n greater than 1. Now let's go to the second question. Let's look at what the phase diagram looks like for infinite n and for finite n. So first, let's start off with infinite n. If you remember, this is what the continuum action for the bulk looked like for the 3D ON model. Here, again, I've split up the phi field instead of living on all of R3 to live on two different half spaces. So there's a phi 1 corresponding to the top half space and a phi 2 corresponding to the bottom half space. Additionally, there's this Lagrange multiplier I lambda, and since the bulk is critical, we tune the coupling here to its critical point. At infinite n, the effective action for I lambda is just a Gaussian of 0 width, so we can just replace I lambda with its saddle point value. Additionally, we know that I lambda is dimension 2, so we know that it's proportional to 1 over z squared because the distance from the defect is our only length scale in this problem. But the coefficient in front of this 1 over z squared has to be such that the boundary conditions for our Green's function is satisfied. So we have 3 different boundary conditions we need to satisfy. One, if you remember in the beginning, where we said that very far away from the defect, the bulk CFT relationships have to hold. That's one of our boundary conditions here, that the Green's function has to go as 1 over 4 pi r, far away from the defect. The second boundary condition is that the fields are equal to each other at the defect. Remember, we just made this, we split up the fields as living, we split the fields into phi 1 and phi 2, but at the defect, they have to equal each other. Finally, if we take one field away from the defect, very far away, this has to go to 0. So it turns out that the values of I lambda that satisfy the boundary conditions take this form where mu is between 0 and 1. And the reason why I write it like this is because the correlation functions look nice as a function of mu when I write it as mu squared minus 1/4. So that means that we can substitute any of these values for I lambda back into our action. And because our action is quadratic in phi, each value of mu corresponds to a different fixed point. And thus we get a line of fixed points for infinite n. We can recover the 3 different universality classes I talked about earlier for different values of mu. The ordinary universality class corresponds to mu equals 0. Special corresponds to mu equals 1/2. And extraordinary law corresponds to taking the limit as mu goes to 1. We can then ask what happens when n is finite. When n is finite, we no longer have a Gaussian of 0 width for our effective action for I lambda. So I lambda is allowed to fluctuate, and it provides 1 over n corrections to our propagators. And I won't go through this calculation because it's a very involved calculation, but we can compute the flow of mu under these corrections, and this is what the resulting beta function is. And as you can see, there's an unstable special fixed point here, and there are 2 stable fixed points corresponding to the ordinary and the extraordinary log universality classes. So to sum up, we get the same phase diagram we had for the boundary case for n equals 2. We get,
For mu is running from 0 to 1.
yeah,
Not clear, but
it's defined here.
yes, so it's by this boundary condition. So what's the physics?
Yeah, so these are the 3 boundary conditions that we had to satisfy. And if you just go through the algebra of computing what the Green's function is, this is what you get. And the values of mu that satisfy those 3 boundary conditions lie between 0 and 1. Yeah. Yeah, so for n equals 2, we have the ordinary, special, and extraordinary log universality class.
Sorry, but if mu is larger or smaller than 0 or larger than 1, it has to.
Okay, yeah. So mu smaller than, so actually, yeah, mu smaller than 0. If you notice that there's a mu squared here, so mu smaller than 0 is the same as mu bigger than 0.
Range from 1 minus 1, let's say.
Yeah, but the 1 and minus 1 are identified with each other.
Above 1.
Above 1, if you notice here, there's exponent, this v over, you have v to the mu over square root of v squared minus 1. And so if mu is bigger than 1, then this diverges as v grows, which is not what we want. Yeah. So this is the phase diagram for the defect, for the 3D-ON model with a defect for n equals 2. And then for all n greater than 2, we still get the extraordinary log universality class. So we answered the second question. We have a line of fixed points at infinite n, and at large and finite n, we recovered the 3 universality classes we talked about. Now let's talk about how these results line up with known theorems of boundaries of 3D CFTs. So to do that, let's first take a detour into 2D CFTs. So for a classical CFT, the stress energy tensor is traceless, and this follows directly from the definition of the stress energy tensor. It's given by -2 over the square root of the determinant of the metric times the variation of the action with the metric. Now let's perform a wild transformation on our system. Let's increase the scale of our system by some value omega. And when we do that, we find that the change in our action is proportional to the trace of the stress energy tensor. And if our theory is conformal, we expect that our action doesn't change under a wild transformation. So we'd expect that the stress energy tensor is traceless. However, a 2D unitary CFT has a trace anomaly given by C R over 24 pi, where C is the central charge, R is the Ricci scalar. Yeah. And now let's consider a theory that flows from a UV fixed point to an IR fixed point in 2D. So in general, these two different theories might have different central charges. And there is a famous theorem by Zamolodchikov that says along an RG flow that the central charge must decrease. And in fact, it decreases exactly by this expression here. We know that this expression is positive because the theory is reflection positive. And here T mu mu, this correlation function is evaluated in a theory slightly perturbed away from the UV fixed point. Moreover, this operator is, if we go back to our setup in the, let me see how to say this. So remember in our setup for the 3D-ON model, at n equals infinity, we get a line of fixed points. So that means at n equals infinity, this operator here should have dimension 2. It should be exactly marginal. So, and then as n is large but finite, this operator no longer is exactly marginal. It picks up an anomalous dimension. Now, how do we compute the trace of the stress energy tensor from this action? Well, under a wild transformation, U changes exactly by something proportional to the beta function, because that's just the definition of the beta function. And so from this result over here, we know what delta S is under a wild transformation. So we should know exactly how to compute T mu mu. And it turns out to be the beta function times O. All right, so that's the story in 2D. What happens when we go to 3D? In 3D, there's only a trace anomaly on a 3D manifold with a boundary. So here, the trace of T is only non-zero along a boundary. And here I'm denoting the boundary as this delta function here. We have a boundary central charge A, and we also have another boundary central charge Vk, just because our boundary exists on a 3D manifold. And so there's some extrinsic curvature K. But we're not going to focus on Bk in this example. Analogously to the example for the 2D CFT, the central charge decreases along a boundary RG flow. And in fact, it's given by a very similar correlation function as the 2D case. Here I've written for convenience T mu mu as script T delta X. just so that we don't have to worry about delta functions appearing in this correlation function. Moreover, if we have a line of fixed points, A must be constant because each of the points along that line of fixed points is both a UV and IR fixed point. All right, so we have this theorem by Jensen and O'Bannon for 3D CFTs, and we want to check that our results match up with that a-theorem. And the way we do that is by taking our theory, putting it on HS3, which is half of a three-dimensional hypersphere, and computing the central charge both directly and from the theorem of Jensen and O'Bannon. The way we can compute the central charge directly is just from the partition function. So remember that under a Wild transformation, the free energy changes by this value here. That's what we discussed a few slides ago. Now consider a Wild transformation where we scale up the radius of our system. Then again, this relationship should follow. And so the leading R dependence of the free energy should take this form, where epsilon is just some distance cut off. When we evaluate this expression on the half sphere, using this expression for T mu mu, we find the following expression for the free energy of our system on the half sphere. So if we know the free energy of our system, we know the central charge. And so we can do this folding trick and compute the partition function explicitly for the different universality classes using the results from earlier, and we can compute the central charges directly. So these are the results that we get when we do that. First, for all n, the central charge of the special fixed point must be 0, because remember, the special fixed point corresponds to the fixed point with no defect. And we know that, as you can see here, this T mu mu is only has a non-zero trace along a defect or boundary. Additionally, we know from our depictions of the different universality classes that the interface or plane defect universality class, ordinary universality class, corresponds to 2 copies of the ordinary boundary universality class. The normal plane defect universality class corresponds to 2 copies of the normal boundary universality class. And the extraordinary log universality class corresponds to 2 copies of the normal boundary universality class, plus the n-1 free scalars that live along the defect. And if we go through this calculation and evaluate the free energy to order, it's a subleading order in n and 1 over n, we get the following results. And moreover, for the boundary, for the ordinary, extraordinary, and special universality classes, we find that a over n goes to 0 as you take n to infinity, which means that as n goes to infinity, we get a line of fixed points. Now let's see if the a-theorem gives the same results as our direct computation. The way we can do it is as follows. So remember, this is the expression for the a-theorem. And remember, we're evaluating this correlation function in the action slightly perturbed away from the UV fixed point. In that case, then the script t is given by beta of u times the O hat operator. And additionally, at n equals infinity, this O hat operator is mentioned too. And so its correlation function takes the following form. Now, once we change n to be finite, the coupling U flows under RG transformations. And so we can use the Callan semantic equation to determine what the 2-point function of the operators is. And it turns out to look like this. That actually should be a U of L and not a G of L. That's a typo. But yeah, so this is what the 2-point function looks like. And we can plug it into the expression from Jensen and O'Bannon. And we get the following expression for the change in the central charge. Now, we can apply this directly to the 3D ON model. And for our system, the coupling that tunes us between the special and the ordinary or extraordinary log fixed points is mu minus a half. Because remember, the special fixed point is at a half, and the ordinary and extraordinary log fixed points are away from a half. Additionally, the operator that tunes between the fixed points is I lambda s. This is a symmetrized version of that I lambda Lagrange multiplier. And the reason why this is the operator that we use is because its bulk to boundary OPE has an operator of dimension 2 at n equals infinity. And remember, we required that this O operator have dimension 2. So once we plug everything into the formula, we get exactly what we'd expect. We get that the difference between the special and ordinary central charges is 1/8, and the special and extraordinary central charges is 9/8. So we verified that our results line up with Jensen and O'Bannon's a-theorem. All right. So yes, the answer is yes to this question. Yeah.
Oh, 2 slides back.
Let's go.
Oh, please. I understand this. So
Yeah. Yeah.
Here, but you have some additional expansion.
Right. So I guess I can talk about how this is derived. So the way it's derived is you couple the theory to some extra field called a dilaton field that removes the trace anomaly from your theory. Then under RG flow, the anomaly should no longer exist. And then you look at the effective action for this extra field. And the effective action for this extra field should exactly compensate the change in the central charge for the fields that were physical. And that's how you get this expression. And I think the way to actually have an RG flow is you have to go slightly away from the UV fixed point. But I think if you so yeah, so I guess it's like slightly away from the UV fixed point. But if you go to this expression here, like in principle, this U is not the UVU, it's U slightly away from the UVU, but we take the limit as it approaches the UVU.
Oh, I see.
Yeah.
So I should just think on the previous slide, you put away and then just even the test.
Yeah. It's just something to start the RG flow. Yeah. All right. So now in the last 10 or so minutes, I'll talk about the different quantum systems that can realize the universality classes that I've discussed, in particular the extraordinary log universality class. So the first quantum system that I will discuss is the dimerized antiferromagnet. So this is a 2+1D quantum system. It's an antiferromagnet with nearest neighbor couplings Jij, and now our spins are quantum spins. And we'll take the couplings along the black bonds to be J and along the red bonds to be JD. So this system has 2 phases. When we can see that as follows. When JD is equal to J, we just have a 2+1D Heisenberg antiferromagnet. And so the order of our system should just be the Néel order. Now, if JD is much larger than J, we'll end up getting singlets on these bonds over here. And so instead of having Néel order, we have just rows of singlets. And thus there must be a transition between these 2 different ground states. And this transition lives in the O3 universality class. And thus we can think about adding plane defect perturbations to the system and see if we get the same universality classes. One way we can add a plane defect is by changing the coupling along a row of spins. and this is just a perturbation to a single row. So in principle, this is like adding a plane defect to our 2+1D system. And thus we should expect to get the different universality classes associated with the plane defect.
You just mentioned earlier you're discussing D+3.
Yeah.
You know, it's +1D.
Yeah, because
You consider in the experiments and earlier is that also quantum system in 3D.
yeah, so because we want under the quantum classical mapping, we want to consider classical 3D ON models. So that means we have to consider 2+1D quantum systems to realize the same universality classes.
And every exponents also carry on.
Yeah. All right. So another perturbation we could add is inserting an extra row of spins. And this is different.
Because D+3 spatial system, you want to consider thermal phase relation, right? You want still consider tuning some coupling that's not thermal, not thermal.
Well, I guess if I go all the way back here. Sorry. Yeah, so here, yeah, I introduced the temperature.
But you want to need a coupling.
Well, tuning the coupling is the same as tuning the temperature, right? Yeah. All right.
So then let me just make sure that why don't we also study starting from this quantum system as more close to experiment instead of doing this quantum system now.
I think so. I think there's interest in just the classical 3D ON model in general. And so I think while there are applications to quantum systems, I think like from a purely like intellectual motivation standpoint, like there's a lot of interest in just the classical 3D ON model.
Yeah, more has been done.
Yeah. 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 All right. So to recap, one perturbation we could add is just changing the coupling along the row of spins, and that's just like adding a plane defect. Another perturbation we could add is to insert an extra row of spins. Now, this extra row of spins is not described by a nonlinear sigma model. There's also a theta term, a topological theta term. And so now our phase diagram is different. We can't just use the same tricks that we used for the plane defect. So just as a brief description of this phase diagram, we can, here JD over J is effectively our bulk coupling that tunes us through the bulk phase transition. G is the nonlinear sigma model coupling. And we get this is a possible phase diagram that we could get. We should expect to get the external log universality class because theta does not enter perturbatively in the beta function for G. Additionally, when G is infinite, there's no order along the chain. There's no like antiferromagnetic order along the chain. So we should recover the ordinary universality class. However, these two different half planes introduce VBS order along the chain. I think there have been some numerical simulations that show this.
So there's a question on the Zoom.
Yeah. Is it in the chat? I don't think I can see the chat. Can you read it out?
So you're asking quantum system with this light effect. Is it periodic in both two directions?
Yeah, we can consider it to be infinitely large. So I don't think the periodicity should matter. But yeah, you can consider it to be periodic in all spatial directions. All right, thank you for the question. Yeah.
But these are bosonic systems. So are there other choices other than periodic or open boundary condition? There's no anti-periodic. Unless you maybe tweak some.
Yeah, you can do some twisting, but yeah, I don't, I guess those boundary conditions are separate from the plane defect. Like that would, like a twisted boundary condition would like be a different type of defect, right? Yeah. All right. So
So we should have joined.
yeah, we can consider it as being infinitely big with open boundary conditions. I think that would be simplest. All right. So yeah, recapping, we've inserted this extra chain here. We have the extraordinary log universality class because theta does not enter perturbatively in the beta function for G. We also have this ordinary VDS universality class. However, this red point here is not necessarily the special fixed point because theta does affect the behavior of the system at this point. So the nature of this point is an interesting question, and it's beyond the scope of this talk. All right. Another system that could realize the extraordinary log universality class is a quantum Hall bilayer. And this was based off of work done by Zhang, Zhu, and Mitrinoff that was put on the archive this year. So consider two fractional quantum Hall layers with filling 1/3 and -1/3 separated by some insulating layer of thickness D. If we apply a sufficiently large displacement field, we will get exciton condensation. We'll get condensation of quasi-particles and quasi-holes. Now imagine increasing the separation D. When D is very large, these two layers are effectively decoupled from each other. So we have a fractional quantum spin Hall state. And when D is very small, we have the exciton condensate. So there is a transition between these two phases. And this is an XY star transition. Star just refers to the fact that the order parameter of the transition is not a physical observable. Now we can think about what the theory looks like on the edge of our system. So recall that a fractional quantum Hall state has edge modes. And these two edge modes are counterpropagating because they have opposite filling. Now consider both the sum and difference of these two fields and integrate out the sum. Then we get the following theory for the following effective action for the difference of those two edge modes. And theta tilde here is just the difference between the two edge modes. Here, phi is the bulk order parameter. So we get this theory, we get this term here just for the theta tilde field. And then this is the coupling of the theta tilde field to the bulk. This term right here is actually just a O2 model for theta tilde because theta tilde is periodically valued. And so the flow of this lambda parameter will tell us what universality class we're in. This paper argues that lambda flows to 0. So this paper argues that this system is on its boundaries in the extraordinary log universality class. All right. The last application I'll mention is yeah. So this is, yeah, sorry, I should have clarified. This is not a defect realization, this is a boundary realization. So the boundary is just like, imagine both of these being like rectangular sheets. The boundary is just the boundary of those rectangular sheets.
But they are similar or the same universality class.
Yeah, so this is the boundary version of the extraordinary log universality class. Yeah.
Does this account for interactions between the two terms?
I think that's all included in this bulk transition here. I think that's what drives the exciton condensation.
Oh, you said that what drives the exciton condensation is the displacement field.
Yeah, but I think the displacement field just encourages it even more. I'm not exactly sure though. Yeah, I think I'm not exactly sure about the microscopic details. I just know that this transition is xy star.
Yeah.
Yeah.
So maybe two things. One is that in the real case, if you have something like a loop into liquid, A states fractional control, and loop into liquid is one plus one B. If you try to add some interaction terms like cosine in terms of some so usually that transition will be more like the BKT both to its colors.
Yeah, so I think
How's that BKT related to X plus star?
so. I think in the absence of this coupling to the so xy star here is referring to the 2 plus 1D transition. Yeah, and then in the absence of this coupling to the bulk, the boundary would act as a 1 plus 1D Ledinger liquid. But since there's this coupling to the bulk, we get the extraordinary log universality class.
And you say these are both transition or H transition or both.
So we tune to the bulk critical point, and then we examine the edge at the bulk critical point. And the paper claims that lambda flows to 0, so we should be in the extraordinary log universality class. Yeah.
XY star transition is the ultimate bulk.
No, xy star is referring to the bulk transition. So that the xy star transition is just, yeah, it's the transition between exciton condensation and fractional quantum spin Hall. All right, so the last application I'll mention briefly is the realization of these universality classes upon applying weak measurements. This is based off of work that was put on the archive this year by Jung-Yeon Lee, John, and Zhu. So the setup is as follows. Consider a state prepared in the ground state of a critical Hamiltonian, and we'll call its density matrix rho naught. Then let's apply some weak measurements to our system. And then the resulting density matrix rho d is just a sum over the outcomes of the measurements of different projections of the pure state on those measurement outcomes. Now, if you want to do some post-selection on the outcome of the measurements, we restrict our sum to be in some set P, and we divide by this trace to normalize our reduced density matrix, or to normalize our density matrix. In the path integral formulation, we can consider the entries of the pure state density matrix as follows. So the phi1, phi2 entry is just a path integral with boundary conditions being phi1 and phi2. When we add the weak measurements and post-selection, we're effectively adding an interaction term between the boundary conditions of our path integral. So this is what it ends up looking like when we apply the weak measurements and post-selection. And if we want to make a measurement of an observable in this post-selected state, we take the trace of the post-selected density matrix with the observable, and we end up with this expression for the path integral. Here, since we're taking a trace, we identify the two boundary conditions with each other. Now let's apply this specifically to the ON model. So we start by preparing a system in the ground state of a critical 2 plus 1D ON Hamiltonian. And then we apply these weak measurements in post-selection. The interaction term we get has to respect ON invariance. And the simplest one we can write down is of this form. When we put this into this action over here, this is effectively just adding a mass to the t equals 0 slice, or tau equals 0 slice. And that is basically adding a plane defect to our system. And so we should realize the different plane defect universality classes along this tau equals 0 slice. And here the sign of epsilon will dictate the universality class. If we add a positive mass, then a positive mass perturbation, we should flow to the ordinary universality class. And if we apply negative mass perturbation, we should flow the extraordinary log universality class. All right, so I've answered the different quantum systems that can realize the extraordinary log. Yeah.
After we do this, we can selection, correlation function, equal time correlation function. The ordinary case will have this extraordinary log.
Yeah. All right, yeah, so that's actually the end of my talk. So in conclusion, this is what the phase diagram looks like for the plane defect 3D-ON model with the plane defect. This is the beta function, and these are the central charges. Yeah.
On the summary, this slide.
Yeah, yes. To recap, we have the extraordinary log universality class for all values of n greater than 1. The beta function looks like this. So we have the special ordinary and extraordinary log fixed points here. And these are the central charges for the different universality classes. And they match up with this A theorem by Jensen and O'Bannon.
Thanks. Thank you, Abijith, for the very interesting result and nice talk. Any question from the audience? Or from the Zoom?
I want to be able to see the chat.
Yes.
Could I be surprised that the difference between these two central charges is exactly like, or is that?
I am not sure off the top of my head.
What this, so this is telling you that the extraordinary log relative to the regular, to the ordinary missing one, right? Smaller than ordinary, right?
Yeah, I was thinking about this last night, actually. I don't know off the top of my head how to interpret it. Yeah.
Actually, I'm not sure. It might not mean anything.
Well, the central charge of a free boson is 1. And we use that. If you go to this slide over here, we use that for this expression for the extraordinary log plane defect. Central charge, we use that. There's n-1 free bosons on the plane defect, and that's how we add this factor of n-1, or this add this n-1 to the normal central charge. So there, I think there is some meaning in the integer value, but I just don't know off the top of my head.
Same like inner discussion. Well, we can talk about. Yeah. Okay. So yeah. Any more questions from line from Zoom? If not, let's thanks Abijith again. Okay.